Describe the surface with the parametric representation. So the first thing I'm going to do is identify the components for the given vector valued function. So we can see here, looking at this vector r, that our x component is defined as v cosine of u. We can see that our y component is defined as v sine of u, and that the z component here is defined as 5v. So again, our job is to identify the relationship amongst these three components. So there again, this is the trickiest part. So one way to help us identify that relationship is to keep those quadratic surfaces in mind and to square each component to help us then identify a relationship. So here we go. We'll square each component in hopes of identifying a relationship amongst them. So squaring both sides of the x component gives us x squared is equal to v squared times cosine of u squared. Squaring both sides of the y component gives us y squared is equal to v squared times sine of u squared. And then squaring both sides of the z component gives us z squared is equal to 25v squared. So looking at these squares here, we can see that x and y have a relationship of v squared. And if we add that together, we could see that Pythagorean identity coming in. We could also see that v squared exists in the z component. So let's see if we can relate all these together. So starting by adding x squared and y squared, we end up with v squared multiplied by cosine of u squared plus v squared multiplied by sine of u squared. Again, we see that greatest common factor of v squared, so we can pull that out to the front, giving us v squared times cosine of u squared plus sine of u squared. And again, we're very excited. We see Pythagorean's identity. We know that that is equal to 1, which leaves us with x squared plus y squared is equal to v squared. So, since we have identified this relationship between x and y, let's now see if we can take this and connect it to our z component. So since z squared is equal to 25 times v squared, we can rewrite this, solving for v squared, to see that v squared is equivalent to z squared divided by 25. So taking this and plugging it into what we just found, we can have a full relationship between x, y, and z. So this gives us x squared plus y squared is equal to z squared over 25. And we can leave our answer like this or group all of the variables on the same side and say that z squared over 25 minus x squared minus y squared is equal to 0. And we're excited because we recognize that this is an elliptic cone. Woohoo! So we have this elliptic cone, and since the z variable is the only variable with a positive coefficient, we know that our elliptic cone will be centered about the z-axis. So the only thing left to do now is to use the bounds to identify what is the height of this cone. So let's keep in mind here, we were given the bounds where u is greater than or equal to 0, less than or equal to 2. So we can see this in our elliptic cone. And the ones that we want to be mindful of here are the bounds on v. So let's think about how those bounds are going to affect this cone. So let's keep in mind we know that v is greater than or equal to 0, less than or equal to 4. And we also know that our z component here is equal to 5 times v. So let's use this equation and rewrite it in terms of v. So I have v is equal to z divided by 5. So we can replace the v in our inequality with this v from the z component. So plugging this into the inequality, we have now that v is replaced with z by 5, so I have that z over 5 is greater than or equal to 0, less than or equal to 4. And if we multiply each part of our inequality now by 5, this gives us that z is greater than or equal to 0, less than or equal to 20. So this is indicating to us that our elliptic cone is bounded by two planes. So it's bounded by the planes z is equal to 0, or the xy plane. And we can see that it's bounded above by the plane at z is equal to 20. And so using this, we can say that therefore the height of this cone is going to be 20 units, or h is equal to 20. So we've used those v bounds to find the height, and we can now use this maximum height to find the radius at the widest point. So we need the radius of the cone at the widest point. So in other words, we want to use the upper bound on z. So z is equal to 20. And so we're going to go ahead here and use the first part of our classified surface. So this is our classified surface here. And so using this first equation and our maximum or our upper bound, we can say that if we plug z equals 20 in, that we have x squared plus y squared is equal to 20 squared, which gives us 400, all divided by 25. And again, I'm plugging this into this first portion of the elliptic cone, which equals 16. So hey, we recognize that this is a circle, again confirming those u-bounds, centered at the origin with a radius of 4. Woohoo! So in addition to the height, the maximum height being 20 units, we can now state that the radius of the cone at the widest point is going to be 4. And we have officially classified the given parametric representation as the elliptic cone centered about the z-axis, bounded below by the xy plane, and above by the plane z equals 20, which tells us that the height of this cone is 20 units, and the radius at the widest point is 4.